I took too much time preparing, so let's get straight to it. Problem 3 intimidates us with a big number, that being 12 digits. But with enough research, this number can be dealt with. Actually, this video isn't going to exclusively be about the Project Euler problem, but some explanation about prime factorization, as well as trial division. Even though this video isn't about that problem, there are going to be spoilers ahead. So, prime factorization, what is it exactly? First, as a recall, prime numbers are numbers that when made into a product, its factors is only going to be 1 and the number itself. 2 is a prime number because the only way to get it is by multiplying 1 by 2. 6 is not a prime number, rather a composite number, because you can get it by multiplying 2 by 3 or 6 by 1. In number theory, prime factorization is a way to express a number as a product of its prime factors. For example, the prime factorization of 250 is equal to 2 times 5 times 5 times 5. There isn't really an efficient algorithm to get the prime factors of a specific number, so we should just do something that would take a lot of calculations. We can start with a factor tree, which is a diagram that finds factors of a number, and then finds factors of that number until it has no more factors that isn't itself and 1. That is, it's a number that is prime. Here's how it works with 360. 360 can be made by 10 times 36. 10 can be made by 2 times 5. 2 and 5 are prime because the only ways you can get them is 2 times 1 and 5 times 1 respectively. 36 is a square number, so it can be made by 6 times 6, and 6 is 2 times 3. We know that 2 and 3 are prime numbers too. Now, at the end of the trail for each path, they will always be prime factors, and the product of these factors gets us to 360. If you don't want to branch our tree, we can go with a more linear form by having one of the factors a prime number. 360 is a product of 3 and 120, and 3 is a prime factor, so we just get straight to 120. 120 is the product of 60 and 2, 60 is a product of 30 and 2, 30 is the product of 10 and 3, 10 is the product of 2 and 5, which are both prime numbers. We still get the same prime factors in our previous tree, so it seems that the factors we choose in order will not affect the answer. With this, we could just change the order of prime factors to an ascending order. As you can see, it still has the same prime factors. The reason why I used a factor tree was to easily explain the algorithm of trial division, a laborious but easy to understand algorithm of getting the prime factorization of a number. Those prime factors here could be known as trial factors, since this algorithm attempts to see if a selected factor is divisible to our number as a trial. If it is divisible, it will continue checking if the quotient is still divisible by that factor. If it is no longer divisible, it moves on to the next trial factor. Here's how someone would code it. After defining the meaning of these variables or initializing the variables, we begin the loop. This while statement states that the code should only end when this condition no longer fits, that is, our number is now less than or equal to 1. Now, it checks if n is divisible with our current trial factor using a modulo operator. If the remainder is 0, then it is a factor, so divide it by the trial factor. We assign the number the quotient and output that the trial factor is one of the factors of the number. Now it will reiterate, is a new number still divisible by the trial factor? If it is, keep dividing it, and if not, you can no longer factor it with our trial factor. So that means we have to move on to the next one, which should be the next integer. By the way, the reason we had to choose 2 as our first trial factor is that if we started with 1, it will continue to loop forever. A number divided by 1 will not change, and since it will only move on the next trial factor if it is no longer divisible by the current one, it will not increment. The loop only ends when our current number is less than or equal to 1. And eventually our trial factor will reach the same value as our current number. If so, a number divided by itself will return 1. So therefore, the number that we divided with must itself be a factor. At the end, we will be given the prime factors. Let's do an example with the number 27,386,100. There is one question though. If we are incrementing through all integers as trial factors, which include composite numbers, why are we only getting prime factors? Recall that in our factor tree, our composite factors can still be extended as a product of prime factors. If we are comparing those composite factors, we are comparing it with previous prime factors. As you can see in our example, there is a set of 2's at the beginning of our prime factors. 2 times 2 is 4, and our original number is a multiple of 4. Our prime factors don't have 4, so you could say the composite numbers are in there. It's just been compressed into prime factors. Though this might be good enough, what if we could make it better? We are searching for prime factors and we know that 2 is the only even prime number. Our trial factors don't have to include all other even numbers if we just separate 2. With this, we could just start with trial factor 3. If it is no longer divisible, increment the trial factor with 2 so it skips to the next odd number. Also, we don't need to do this for all odd numbers below our current number. We can stop the loop once the square of our current trial factor is greater than our number. And you might ask why. If n is an integer, n can be expressed as p times q, where p and q are integers. N can also be expressed as the square root of n multiplied by itself. Now, let's imagine that n is the number 64. Here are a list of values of p and q in this case, where the left column shows values of p and the right column is its corresponding values of q. Notice that 8 is the square root of 64, and anything beyond 8 times 8 is just a repeat of the possible solutions preceding it in a different order. That means that anything beyond it is repetitive and should not be checked. But anyway, it would be impossible for it to be checked because the first factor will always be checked, and since n is reassigned, the factor list changes. So now in our code, there's one last thing to check, and that is to print our number if it's not equal to 1. Since it's been divided so many times that there aren't any more factors, the remaining number should be a prime factor or just 1. Also, it can't be 2 either. In the end, our output would be a list of prime numbers. With that, we just got rid of at least half of the calculations we need. In conclusion, that took a while.